Hello, this is Eric Beichel, Senior Application Engineer at Altair. Today, during this video, I'm going to walk through the explanation of coupling EDEM, HyperStudy, and MotionSolve. What I'm showing on my screen now is a file path that contains the EDEM and motion models. I'll point out that the file path must not contain any spaces because HyperStudy doesn't appreciate spaces. Opening up the motion model, I'm just going to verify that this model will run before coupled to EDEM. So clicking on the run and looking at the console solver view, you can see that the time is progressing and that we get the generated output from the model, the H3D file that you can use for visualization of the movement of the geometry, and the PLT file that you can use to extract plotted data from the simulation. Next step is to create the EDEM subsystem. So I'm selecting bodies after and including all of the bodies using a group select. Now I will switch over to EDEM and open up the deck that's pre-populated with everything but the geometry. So the factory is in there already, just waiting for geometry, and I'll enable the coupling server. Switching back to motion, I will go ahead and click the transfer and create system. Bringing EDEM back into focus, we can see that the geometry is imported in EDEM through the coupling, and that we've successfully imported all 20 geometries. So now I'm looking in the data set to verify that the communication interval is at a factor, an integer number of the time step. So in the EDEM simulation, I'm running at 1/10,000th of a second. Communication interval is at every 1,000th of a second, so that is okay. The next step will then be to launch the coupled simulation to verify that the simulation will run without failure. Before we do that, I'm just pointing out here that the save interval I'm using is 100th of a second, and I am using selective save, only including, with the check mark, the base particle data and base geometry data to minimize the file size that's created from these simulations. Switching to 8 CPU solvers, I'll save the EDEM deck with the coupling server enabled. I'll switch back over to motion and kick off the coupled simulation. Oh, also pointing out that the update in EDEM, I've disabled the automatic update so as to make EDEM run as fast as possible. In this case, I'm going to run for 20 seconds with a save interval of 0.05 seconds. So we've already seen that the simulation has progressed at 0.2 seconds, which is positive. We've got particles going in there. Just cut to the end of the simulation where you can see that the output files from motion were generated, which is positive. And then also I'm pointing out here that in the AND list, there's already a pre-populated export data CSV file that will be generated with 3 outputs: the mass of the large particles in the upper bin, the mass of the smaller pills in the lower bin, and then also there is a sensor that's at the discharge of the upper bin that's going to count the number of smaller yellow particles discharged. Now, for this particular system, what we want to happen is all of the yellow pills to drop out the bottom and none of them to drop out the top. So the export data is the CSV file that is generated from the EDEM output. And I'm just pointing out here that we've got the PLT and the H3D file output from the motion model. Now I'll open up the EDEM export and just show you what that looks like. We've got a time column and then the chunks in upper, pills in lower, and sift failure. That's the number of small particles exiting the top of the sifter. So that's all of the outputs that we need for the simulation. Now we're ready to proceed forward and kick off the coupled simulation within HyperStudy. So I'm doing here is rewinding the simulation to the 0th time step, saving the deck, and also saving the motion model, closing both files. We'll then bring up a new study in HyperStudy. In this case, I'm calling it Sifter example, and I'm going to place that in the same directory where I had placed the EDEM and motion files. Just verifying the location of where I've saved it. Add in the motion model. The motion model, I'm going to, in resource, select the .mdl file, not the snapshot. The snapshot's generated after you run the model, going with the original model. And now I'm copying and going to paste in the solver input file the name of the MDL, but change the extension to XML. Going to switch the solver execution script to none, and then I'll go ahead and import the parameters. So this is going to open up the motion model, and it'll open up an additional window that will allow me to select the variables that I want to control through HyperStudy. In this case, they're nested inside the data sets, and I have motor control parameters that I want, specifically motor speed, so selecting the value and hitting add, and then the weight parameters, I'm selecting the weight upper mass, adding that, the lead angle value, adding that, and the upper distance from center, adding that. Note that the other parameters in there that are related to weights are parameterized in the motion model themselves, meant to be equal to the upper weights. That's why we're only picking the upper, not the upper and lower. Switching over to the variables, you can see that they were pulled in from the model. The next step will be to run this model so that the M1 folder is generated. That M1 folder will always have a red error associated with it because there's no solver execution script associated with it. It's not a problem. But the important thing that we need from M1 is this XML file. That's going to be an output file that will link into Model 2. That will become clear here in just 1 minute. So we need to add in model resources. In the model resources, we've already added that MDL by selecting that, but we need to pull or create an output file, the XML. And then we'll also pull in the graphics file. So that's adding a model resource input file, and we're specifically looking for the ms input gra graphics.xt file. We're going to copy that. Now, M1 should be ready to go. We can set the data type and the ranges for the values that we want to include in our study. So in this case, I'm adjusting the values from 600 to 1200 for motor speed, for upper weight mass. Somewhat struggling here to actually just put in a 2 to 3 kilogram mass range. There we go, 3. Apply. The lead angle will change from 0 to 60 degrees. We'll go with 5 levels. And upper distance from center will go from 50 to 125 and 4 levels. So the parameters are now set. They're integer, discrete. The ranges were set. Now the next step will be to add the EDEM model. So adding another model, EDEM, selecting the EDEM deck that is in the same folder. Now in this case, the solver input was pre-populated, and we're just going to add in a -C0, CO, I should say, not C0, CO, and the name of the solver input file from M1. I've selected import, And this is just for demonstration purposes. I'm going to include just the environmental gravity X value for demonstration purposes, but in this study we won't actually control anything in EDEM directly through HyperStudy, so I'm going to disable this. The other advantage of importing those variables using the EDEM HyperStudy connector is that when we go up to the model resources, you'll see that the EDEM files have already been added. Though we do need to add some more files here. We need to take the output from model 1 and link it to model 2. So in that case, we will select EDEM and add a link. In this case, there's only one file that we can select, the output from model 1. It's our XML file. And in order for that model to run, we also need to add the graphics file. So we're going to add an input file and pull in the ms input gra.tx file, sorry, XD file, and copy that into the same directory. So now we'll kick off this first run and verify that the simulation will run, the coupled simulation will run when started from HyperStudy. In this case, I'm going to delete the output files that have been previously generated. Recall we already populated some files into M1. You can check and verify in the data output that files are being written in the EDEM data folder, so that's great. Now after that output file is generated, we should also see some output files in the form of the motion files, H3D file and PLT file, and also the export data that was generated from EDEM. So that's great. Now we need to define the output responses. And in this case, we will be taking output responses from both motion and EDEM. To define the output responses, we'll first define the data sources. First data source that we're going to pull in is coming from motion. So going to the M2 model and pointing to the .plt file. We're going to take in time. We'll add another data source that's coming from the same PLT file in M2. But in this case, we're going to change to displacement. And we want to change the component to Sifter. We want X. We'll add yet another one coming from the same PLT file, displacement, Sifter, and we'll switch to Z. And we'll add one more coming from the motion model using that same file, going displacement, Sifter. In this case, we're going to take phi, PHI. Now we will add in the model, sorry, I should say data source from EDEM. In this case, it's a Python script. I'm just going to copy and paste in the pre-populated Python script that I've got. And this is just a clever way of pulling the last time step data. I'll also point out that I've pointed to the export data, the CSV file in the top right corner by hitting the folder, not shown in the video. So the next task is to now define the output responses. So the first response that we're going to include is coming from EDEM, and this is going to be the chunks remaining, defining a variable name without spaces, and the expression is just going to be extracting from the data source, EDEM data, the first element. See, it's failed here because I don't have the variable names specified correctly. I'll need to update the variable names for all of the data sources. Oh, mistakenly put EDEM data on the fourth, not fifth, but time for the first, Sifter X displacement, Sifter Z displacement, and then we're saying Sifter phi and EDEM data. Now, I still have a mismatch in the case. the DEM needs to be a lowercase in this example, updating that spelling discrepancy. I can now see that I've pulled in the first element of that array. It's 21. Next output response I'm going to define is the pills remaining no space, and EDEM data second value, evaluating and pulling in 47 successfully. The third output response, sift failures, failure, and that'll be the third and last element of that array. Now I'll add in the response from the motion model. In this case, I will first define the vertical amplitude of the drum as vert amp, and I'm going to, in the expression, leverage batch polyfit that has an input of time and Hilbert, and in this case it's the Z displacement that I'm after. I'll then add in the last two output responses that will be coming from motion, the horizontal amplitude of the drum, using the same batch polyfit, leveraging time and the Hilbert function, and finally the pitch, using that batch polyfit time and Hilbert. Now I just needed to update that last input from 2000 to 400 because we were running at 20 seconds and a 0.05 second write-out period, so we have 400 data sets for each one of these. So we've updated all of the output responses. Now I'm setting the targets. We want to minimize the number of sift failures and minimize the pills remaining and chunks remaining. Our first target is to minimize failures, but ideally we want to minimize the chunks remaining, which is another way of saying we want to maximize the output of the sifter. The next step is to add in the optimization. So I'm referencing the setup that was already run. In this case, I'm just going to use the global response search method, and I will reduce the number of evaluations down to something a little bit more manageable for this demonstration of 50. In order to have successful co-simulations, we need to go in and adjust within the evaluation parameters the delay between runs. I've set this to 20 seconds, 20,000 input. This ensures that the co-simulations run successfully. I'm going to set up, instead of 4 jobs to run in parallel. In order to have 4 jobs run in parallel with the resources that I have, I'm just going to open up the EDEM deck and adjust the number of CPUs to 4, saving that and closing it. So I'll hit evaluate task, and then we should see that 4 models are generated. The execution failure, that is going to happen every time, again, because model 1 has no solver. So don't be alarmed by that. I'm now just checking to make sure that we see progression in the data folders in M2 of run 1, run 2, run 3, and finally run 4. Yes, all of them are progressing. Now the optimization has run to completion. In total, there were 40 iterations run, and I'll just switch over to the evaluation plot and recall that we wanted to have sift failures minimized, so 0 would be the value that we're after, and then also we'll take the pills remaining, the minimum value that corresponds with a 0 failure. In this case, you can switch over and you can see that it's number 23, so 0 sift failures. We've got 95 pills remaining, 32 chunks remaining, and that was achieved with a 50 offset, 0 lead angle, and 3 kilogram, the max weight, and 1200 RPM, the max speed. Now here's the results of that optimum simulation. Again, we're trying to get all of the large green components to drop out the top and all of the yellow smaller components to drop out the bottom on the left-hand side. Now, point out that from this optimization, there are no failures, but there is still some material that's left in the sifter. Perhaps changing the discharge chute over where my cursor is to a downward sloped would improve that situation, or perhaps the bounds of the parameters that were used in the optimization could be extended to improve its performance. But in general, that covers the coupling of HyperStudy, EDEM, and Motion to optimize the Sifter performance.